So far we have seen, so we have a, if you have a system and you are giving a force, this force, if you giving a periodic signal, and you can, if you try to find x of t for this, the one way of is writing in terms of convolution integral. So the other way of writing is this is one way. The other way is you write this, you convert this aperiodic into periodic and take Fourier series, then you directly substitute it into the equation, or this is one way, direct substitution. Otherwise you take Fourier transform. So you take Fourier transform. So what happens, you take Fourier transform of everything. So this x of t equal to, so you take Fourier transform of every terms, so which include mx double dot cx dot plus kx equal to f of t. If you take Fourier transform, so this is Fourier transform, then you will get x of omega equal to h of omega equal to f of omega. So whereas h of omega is equivalent to 1 divided by 2 pi of 2 pi 1p here. So x of t e power I omega t dt. So similarly f of omega equal to f of t e power I omega t dt. So now we don't know what this h of t. So how to calculate this h of t? So this h of t is independent of what? Independent of forcing, independent of force. So this one is called dynamic stiffness, and it contains characteristic of the system. So whatever the force, so it will, depending upon the force, it will transform that force and give in terms of displacement. So we have delta function. So if you take Fourier transform of delta function, what you will get, if you have a delta function and you are giving into the system, so what the response you get the response of h of t, which will be like this, right? Whereas delta function is at t is equal to 0, you have delta of t. So now if you take Fourier transform here, also you are taking Fourier transform. So what this will get converted, this becomes 1 divided by 2 pi. So because then similarly this is the system. So this, if you get Fourier transform of h of t, it will become h of omega. So therefore we conclude this h of t and h of omega is Fourier transform pair. From definition, so definition of Fourier transform, this x of t and x of omega is Fourier transform pair. So therefore now we know how to fully convert the system from time domain to the frequency domain. So I will write the summary of so far we have seen. So we have a system with the forcing f of t with the boundary condition x of 0, x naught, x dot of 0, x dot naught. So if you solve this, so what you will get, x of t in time domain. So this will be the complete solution. So where this h of t is e power minus neta omega t m omega d sin of omega dt, and this g of t will be e power minus neta omega t 1 minus cos omega dt plus neta divided by 1 minus neta square sin omega dt, and yeah, that's it. So now this is time domain equation. This is time domain equation. So where is frequency domain? It will be easily represented as x of omega equal to h of omega f of omega. For that you need to take Fourier transform of time domain elements individually, then you need to substitute in this equation. So these g of t, response of unit impulse, unit step function, h of t response of impulse, and h of omega, these three things. So these three things is powerful description of dynamical system. So every subject has some awe factor. So you can, after knowing those things, you will say, wow, it's great. So one such thing is this g of t, h of t, and h of omega. So this one, so where h of t will be dg by dt, h of omega is Fourier transform of h of t. So why this is very important? If you have any system like some cantilever or some tank, water tank, so in order to know how it will behave at which frequency, that means how to find this x to get this h of omega. So if we know h of omega, then we will know how it will we will know its natural frequency. So and we will know this graph. So this graph is very much important to understand the system so that we can design. So this thing you will get with very small experiment. So where you place one sensor here and here, then you go to the top of this water tank, and with the large hammer you hit it. So when you hit it, you will create a signal like this. So this time period, this has some forcing time. Okay, if this time period is far less than natural frequency of the system, then this will be considered as impulse function. So it should be like 1/10 of the natural frequency. So 1/10 of this time period, first natural time period. So then it will call impulse. So once you given the impulse, you will get the function which response like this, which is called h of t. Now you take Fourier transform. you will get dynamical stiffness, which will give every information the system has, that will help us to design the system and understand the system better. This is our factor in this course.